So let us continue with our discussion on connectedness. So the main result we are going to prove today is the following theorem. So let X and Y be connected topological spaces. Then the product X cross Y with the product topology is connected. So let us prove this. So let us assume that X cross Y is not connected. Right? So then there are open subsets, non-empty open subsets A and B such that this product is the disjoint union of A and B. Okay. So in the previous lecture, we saw that the image of a connected topological space under a continuous map is again connected. Okay. So the precise result was f is from X to Y, X is connected, then f of X with the subspace topology from Y is connected. So let us use this result. So we look at the map from Y to, so fix X naught in X, right? So fix an X naught in X, right? And consider the map from Y to X cross Y given by Y maps to X naught comma Y. Right. So to check that this map is continuous, we just need to check that both the factors, the projections to both factors are continuous. The projection to the first factor is just the constant map which sends everything to X naught and therefore it is continuous. The projection to the second factor is the identity map which is continuous. Right? So this map is continuous. And has image equal to the subset X naught cross Y. Right? So therefore applying this previous result, so thus X naught cross Y with the subspace topology, since Y is connected, is connected. Right. So now let's look at, we intersect this equation with X naught cross Y. So we get X naught cross Y is intersected with A. This is an open subset of X naught cross Y in the subspace topology, disjoint union intersected with B. Right. So if x naught cross y intersected A is non-empty and x naught cross y intersected B is non-empty, then we get a contradiction. A contradiction to the connectedness of x naught cross y, right? Right. So therefore, one of these has to be empty. So this implies that x naught cross y is contained in A or in B. It's completely contained either in A or it's completely contained in B, right? So, right. So similarly, so this happens for all x naught in x, right? So given any x naught in x, when we look at x naught cross y, that subset is completely contained either in A or in B, right? And so similarly, arguing in the same way, for every y naught in y, the subset x cross y naught is contained in A or in B, right? So now we can get a contradiction as follows. So choose any. So since A is non-empty, let x naught comma y naught be a point in A, right? So right. So suppose our point x naught comma y naught is here, right? So then if we fix x naught, so this is the line, this is x naught, right? This is x naught cross y, right? So this implies that, so since x naught comma y naught is contained, so as x naught cross y is contained in A or in B, and it has a point, and x naught comma y naught, which is in a point in this x naught cross y, is in A, this implies that this entire line x naught cross y is completely contained inside A, right? Now we can take any point, let's say y1 over here, and we can argue in the same way. We can look at the line, this line, right? So this is y1 and this line is x cross y1, right? So this implies, okay, for any y in y, x naught comma y is contained in A, and since x cross y is completely contained in A or in B, and it has this one point x naught comma y. Okay, so instead of y1, let me just take this point y. Right, this is this point y. So this point is contained in A, and this entire line is contained either in A or B, but this line contains this point which is in A, so which forces that, this implies that x cross y is contained in A, right? And this happens for every y, for every y in y, right? So this implies that x cross y which is equal to the union of x cross small y is completely contained inside. Yeah, but this contradicts. But this shows that B is empty, which is a contradiction. Right. So thus, x cross y is connected. Okay. Okay. Right. So as a corollary, we see that Rn is connected. Okay. Right. So inside Rn, so okay. So let's see some applications of the results that we have seen so far, right? So we just showed that this corollary Rn is connected, and as an application, right? So there is no surjective continuous map f from the interval 0, 1 to, let's say, the interval 0, 1 disjoint union the interval 3, 4. Right? Why is this? Because if there was such a surjective continuous map, then it will force that the image is connected. But clearly, since the map is so if such a map existed, then since it is surjective, this will imply that 0, 1 disjoint union 3, 4 is connected. But clearly that is not possible. This is not possible. Right? Because if we let x equal to this disjoint union and we let this to be u and this to be v, right? So then both u and v are open in X, right? So X obviously has, I mean, we are giving X the subspace topology from R, right? Has the subspace topology from R. Right. So in particular, these two spaces cannot be homomorphic. Okay. Another simple observation is that if X and Y are homomorphic topological spaces, then X is connected if and only if Y is connected. Right. So this is easy because if f and y are homomorphic, that means there is a continuous bijective continuous map from x to y, right? So therefore, the image of f is all of y, and since x is connected, so that means y is connected, right? And conversely, if you are given that y is connected, then we can take the inverse of f, right? G, and yeah, once again, since the image of G is all of x, it will mean that x is connected. Okay. Now, the next application we have in mind is to show that the spheres are connected, but for that we need the following lemma. Right. Let T1 and T2 be connected subspaces of a topological space X. Right. So, assume that T1 intersection T2 is non-empty. Right. Then the union T1 union T2 is non-empty. Right. So, yeah. So let's prove this. So let us assume, if possible, let T1 union T2 be not be connected. Okay, be disconnected. Okay, so let's say our T1 is like this and T2 is like this. Right. So that means we can write T1 union T2 is equal to T1 union T2. So let's call this space Y. So since we are assuming that Y is disconnected, so we can write Y is equal to, there are two open subsets, so every open subset looks like Y intersection U, where U is an open subset of X, disjoint union Y intersection U, V, right, where U and V are open subsets of X. Okay. So let's take a point in the intersection. So let A be a point in the intersection, which exists because we are assuming that the intersection is not empty, right? So then A is either in Y intersection U or in Y intersection V, right? So assume that A is in Y intersection U. Okay, so since now let's look at T1, right? So intersecting this equality with T1, we get that T1 intersected U, disjoint union T1 intersected V, right? Now T1 is connected. As T1 is connected, one of these has to be empty. That is, T1 is completely contained in U or T1 is completely contained in V, right? So since T1 contains A and A is in U, right, as A is in T1 and A is in U, so this implies that T1 is completely contained inside U, right? Similarly, as A is also in T2, this implies that, and T2 is also connected, so repeating the same argument with T2, this implies that T2 is also contained in U, right? But then this implies that Y, which is equal to T1 union T2, is also contained in U. Right? So this implies that this Y intersection V has to be empty. Right? Because Y intersection U is equal to Y, so therefore this is forced to be empty. Right? This is a contradiction. Right? So now let us use this lemma to show that the spheres are connected. So corollary of the lemma, Sn is connected. Yeah. So to show this, recall that. So recall the map projection from a point. Right, and using this map, we had shown that using this map, we had proved, this was left as an exercise actually. Using this map, we can show that, so this map is phi from Sn minus, so let's make a picture. So we are taking this sphere, we remove this north pole, 1 point, and then we project to this plane. Right. So we have shown that this minus 2Rn is a bijective continuous map whose inverse is also continuous. Okay. So let psi denote the inverse. Right. So as Rn is connected, so let's call this inverse, let's call this psi 1. Okay. As Rn is connected, this implies psi 1 of Rn, which is equal to this sphere minus this north pole is connected. Okay. Now similar to projecting, removing the north pole, we can, instead of the north pole, we can remove the south pole and project once again. Right. So let's call this map phi 1. Yeah. Similar to this map, to phi 1, we have a map phi minus 1. This is from the sphere, so we remove the point, the south pole, to Rn. Right. So geometrically, what does this map do? So we have the sphere, we are removing this point. Given any point on the sphere, so this point is P and this point is X, we join P and X with a straight line, and X is sent to the point Q. Right. So this is our Rn. This is Sn minus 1. Right. So in the same way, we proved that phi 1 is continuous, is bijective continuous, with continuous inverse, we can prove that phi minus 1 is bijective continuous with continuous inverse. Okay. So let psi minus 1 denote the inverse of phi minus 1. Right. So then psi minus 1 of Rn is connected as Rn is connected, right. So, our Sn, we can now write it as psi 1 of Rn union psi minus 1 of Rn, right. So, psi 1 of Rn is Sn minus this north pole, and psi minus 1 of Rn is Sn minus this south pole, right. So, as both these intersect, so let us call this T1, or we don't need as Sn minus the north pole and Sn minus the south pole have non-empty intersection, and these are connected. The previous lemma implies that Sn is connected. Yeah. Of course, always n is greater than or equal to 1 over here. Okay. So, that is a nice application. So, we will end this lecture here, okay, and in the next lecture we will continue with connectedness.